Imagine you are managing a massive warehouse where goods arrive and leave at a frantic pace. If the system tracking inventory is slow, the whole operation grinds to a halt. In the world of computer science, memory management is exactly that warehouse. When artificial intelligence models run inference tasks, they demand memory in unpredictable bursts. Standard systems often struggle to keep up, leading to slowdowns that can ruin user experience. This is where the story of Meta and their long-standing relationship with a specific memory allocator comes into play. The renewed focus on this technology signals a strategic pivot from reliance on external tools to a deeply integrated, custom-built memory management solution optimized for their specific workload patterns. To understand why this matters, we have to look at how computers handle memory today. Most software relies on a standard library allocator. This is the default tool that every programmer uses without thinking about it. It works like a generic storage system. When a program asks for space, the system gives it a chunk. When the program is done, it returns that chunk. In simple applications, this is fine. But in high-concurrency machine learning inference, the workload is different. It is not simple. It involves thousands of threads competing for resources simultaneously. When many threads ask for memory at once, the standard allocator becomes a bottleneck. Here is the thing that often gets overlooked. Standard allocators were designed for general-purpose computing, not for the extreme demands of modern distributed systems. They suffer from synchronization overhead and cache pollution. Synchronization overhead means that threads have to wait for each other to access shared memory structures. It is like a single checkout lane at a busy airport where everyone has to wait in line, even if other lanes are empty. Cache pollution occurs when the memory system gets cluttered with data that is not immediately useful, slowing down the processor. This happens frequently during high-concurrency spikes where the system is trying to process thousands of requests per second. Meta has recognized that these bottlenecks have become critical performance constraints. This realization necessitates a return to foundational infrastructure improvements rather than higher-level application tweaks. They are not just tweaking code on top of the problem. They are going back to the source code of the memory management layer itself. This is where jemalloc enters the conversation. Jemalloc is an open-source memory allocator that has been around for a long time. It is widely used, multi-threaded, and optimized for performance. But the renewed commitment suggests that Meta is not just using it as is. They are likely integrating it more deeply into their infrastructure to handle the specific patterns of their machine learning workloads. Let us compare how jemalloc behaves versus a standard allocator during a spike in traffic. Imagine a sudden influx of users loading a new video feature. In a standard system, the memory allocator might struggle to find contiguous blocks of free memory. This leads to fragmentation, where free space is scattered in small pieces rather than large chunks. Fragmentation forces the system to search longer for space, increasing latency. Jemalloc handles this differently. It uses a technique called slab allocation. Think of this as pre-sorted bins for different sizes of items. When a request comes in, the system knows exactly where to look. It does not have to search the entire warehouse. This reduces the time it takes to allocate and free memory significantly. Furthermore, jemalloc is designed to minimize the synchronization overhead we discussed earlier. It uses thread local caches. Each thread has its own small stash of memory ready to use. This means threads do not have to wait for a central lock to grant permission. They can grab what they need instantly. When the local stash runs low, they request more from the global pool in a way that minimizes contention. This is crucial for machine learning inference where latency is key. Every millisecond counts when you are serving real-time responses to users. The research into modern allocators shows that this is not just about speed, it is about predictability. In high-performance query processing, you cannot afford the variability that comes with standard allocation. The variability creates pauses that users notice. These are often referred to as garbage collection pauses or allocation stalls. By investing heavily in jemalloc, Meta is prioritizing fine-grained control over memory fragmentation and latency. This often comes at the cost of increased engineering complexity. Building and maintaining a custom allocator requires deep expertise and constant vigilance. But the payoff is a system that can handle massive-scale, multi-threaded applications without the stuttering that plagues standard library allocators. This decision reflects a broader industry trend where high-performance systems prioritize control over convenience. For a long time, developers were told to use the standard library and focus on application logic. But as systems scale, that convenience becomes a liability. The consensus among researchers is that a one-size-fits-all standard library allocator is insufficient for these demands. Custom, more heavily tuned allocators like jemalloc are essential for maintaining throughput and reducing garbage collection pauses. This is why we see a shift towards formal verification and security-oriented designs in allocator research as well. Concepts like star-malloc suggest that future systems will not just be fast, they will be proven to be correct and secure. The implications for the future are significant. Meta's internal optimizations and formal verification efforts will likely drive the next generation of open-source allocator standards. This means that the improvements made for their specific needs will eventually influence how large-scale distributed systems handle concurrency and security. It is a ripple effect. When the largest players in the industry optimize their infrastructure, the tools and techniques they develop often filter down to the rest of the ecosystem. This raises the bar for what is considered acceptable performance across the board. It is also worth noting that this focus indicates that existing memory allocation bottlenecks have become critical performance constraints. The industry is reaching a point where higher-level application tweaks are no longer enough. You cannot optimize your way out of a fundamental infrastructure limitation. You have to change the foundation. This renewed focus on memory allocation is a signal that the era of ignoring low-level details is over. High-performance systems now require a deep understanding of how memory is managed at the hardware and software interface. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.